Welcome back to Applied Mathematics. In this video, I want to talk about numerical tools for solving systems of linear equations. Before I get into the how, I want to talk a little bit about the why. There are some obvious advantages and also a couple of disadvantages to using a computer in order to solve a system of equations for you. The obvious advantage is that it can be faster. And I do have to stress there can be. For a simple equation or a simple system, two equations and two unknowns, generally speaking, once you know what you are doing, it's faster to solve on paper than it is to boot up the computer, get to a place where you can solve a system, enter the system into the computer, and then interpret the solution. But computers scale beautifully in the task of solving systems of linear equations. This is probably the thing that we best understand how to get computers to do for us. So if you have a system of three equations and three unknowns, the computer's not going to take that much longer, where trying to do it by pencil and paper is going to take a lot longer. 4 by 4, even more. 5 equations and 5 unknowns, now you're getting to the point where trying to do this by hand can be painful. 10 equations, 10 unknowns, there is no way I'm going to try to solve a system like that using pencil and paper. The disadvantages do exist though. First of all, we can't really say that we are finding the solution. When we're using numerical tools, we can best say that we are approximating the solution. In a lot of cases, that's perfectly fine. We have talked enough about the significant figures rule for approximations to know that when we have approximate values going into the system, all we can expect is approximate values coming out of the system anyway. That's not anything that is a major hindrance. The other obvious downside of trying to use numerical tools is that you have to have a computer. In artificial situations like being in a classroom where there is no computer, well, there's no computer. But that also occurs in the workforce as well. There are often going to be times when you are dealing with trying to do computations and getting to a computer to have the computer do the calculation for you is an endeavor. It's not something that just is readily available. And the last and probably the most important is a little bit beyond the scope of this course, but for anyone who is continuing on in their study of mathematics. We are really good at getting computers to solve systems of linear equations. We are really not good at getting computers to solve systems of nonlinear equations. The pencil and paper approach for nonlinear equations is incredibly similar to the pencil and paper approach for linear equations. So learning this as a scaffolding trick of once you know how to do this for linear equations, I don't know what just happened up there. Once you know how to do this for linear equations, you know how to do this for nonlinear equations, and it's going to make your life easier moving forward. All right. So all of that out of the way, let's get into how this works. All right, so let's start off with this system of three equations and three unknowns. X plus y plus z equals 6, 2x plus 3y plus 5z equals 23, 3x plus 2y plus 4z equals 19. In order to have a computer system solve this equation, the first thing we're going to need to do is to create what's known as the matrix representation. A matrix is a way of arranging numbers in a structure that gives it the ability to work for us in many different ways. If you're really curious into the mathematics behind matrices and matrix representations, the branch of mathematics called linear algebra is the study of matrices and things that can turn into matrices. For our purposes, though, we're just going to accept that this is a thing we can do. And specifically, we're going to need two matrices. We're going to need the coefficient matrix, and we're going to need the constant matrix. Again, the details of how these are used are well beyond the scope of this course. I don't want to get into it, but finding them and understanding them is not that bad. Remember that a coefficient is a number being multiplied by a variable. And in fact, that's kind of our goal. If I look at my system of equations, one of the things that we notice whenever we have our system set up in the standard form, we've got all these x's and y's and z's hanging out with each other, and they're always in the same order, and they usually have a coefficient in front. This first line doesn't really, but remember, we can always fill in, right? 1 times anything is that thing, so we can think of that as 1 times x, 1 times y, and 1 times z. Then as a shorthand, when I know that this is the structure of a system of linear equations, I can just write down that that first equation is 1, 1, and 1. 1 times x, 1 times y, 1 times z. The second equation is 2, 3, 5. 2 times x, 3 times y, 5 times z. And the third equation is 3, 2, 4. That is our coefficient matrix. We usually put square brackets or sometimes parentheses around a coefficient matrix or around any matrix just to indicate this is a matrix. And then we have the constant matrix. When we have our system of linear equations in the standard form like we do here, the right-hand side of the equation of every single equation is going to be a constant. We can list out all of those constants in their own matrix. 6, 23, 19. And with those tools, we have the information that we need to write the matrix representation of the system. All we do is we take our coefficient matrix, we multiply it by, most textbooks will represent this with a bold letter x. In order to get a bold letter x when we don't really have the ability to write in bold, we often put an arrowhead above it. The hows and whys of that are not very important right now. But if we take the coefficient matrix and we multiply it by a bold x, we get the constant matrix. And that's the way that linear algebra understands a system of linear equations. And with just that, we are now ready to start thinking about how to tell a computer what to do with this system of equations. All right, so for that, I'm going to jump away from my notebook and over here into this Jupyter notebook. Depending on the order of topics, which I shuffle from year to year, you may or may not have already encountered Jupyter notebooks. But Jupyter notebooks are a nice way of working with the Python programming language. And the Python programming language is my favorite way of trying to get computers to do just about anything. The first thing I want you to know is that when you're in a Jupyter notebook, and I will be sharing this notebook with you so that you can open it and modify it. I'm running this in Google Colab, which is available for free to anyone who has a Google account and your Westmoreland issued email address is a Google account. right? But I'm going to go to File, and I'm going to say Open in Playground mode. This allows me to modify the notebook without having to worry about changes being saved. So the original file will be how it is, and any changes that I make won't get propagated, and that way I can save this and share it a little bit more nicely. It gives us a nice warning to that effect up here. I can make it go away so we have a little bit more space to actually read the text. Although the text is a little bit small, so let me see if I can make this a little bit bigger. I am not sure if this is going to work. All right, I think that's a little bit closer to readable. And again, you should be able to open this, so if you can't read it very well, that's not a big deal. All right, but we're going to use the NumPy package, Numerical Python, which has built-in features for dealing with a lot of repeated calculations, like solving a system of equations. All right, so the first thing we need to do is import NumPy, import Numerical Python. In the second block, I explain out a little bit more of what we're going to be doing here. This is the same explanation that I just went through in the Scribble notebook that we were looking at. But then we come down here. Modify this section to represent your measurements. So we have our coefficient matrix, which we're calling A in this case. And you can see here that it is set up for us. And I've already put in the particular example we were looking at. Our first row was 1, 1, 1. Our second row is 2, 3, 5. Our third row is 3, 2, 4. The way that NumPy handles arrays. First of all, we need to tell it we have an array, and we need to open up square brackets because we surround matrices with square brackets. But then whenever you have more than one entry in a row, you have to put that itself inside of square brackets. That's the way that NumPy can handle things. Separate each value with a comma, separate each row with a comma. The constant matrix, we don't need to worry about the extra square brackets because there's only one element in each row. Just separate each row with a comma so it goes across a line instead of down a column, but it's the same idea. Once we have that, we then have this last thing, which is the instruction to solve the system, right? Solve using linear algebra that we got from the NumPy package, and then print out the result. All right. My instructions tell you to now go to runtime and restart session and run all, but you can see that that's grayed out right now because I haven't done anything yet. So the first time we do it, we're just going to hit this run all. It will take a little bit of time, and it will spit out our solution. Our solution in this case is 1, 2, 3. And if I jump back to my Scribble notebook, I can write out that solution. In vector form, we're going to say that x is the vector 1, 2, 3. And then we can interpret that to mean that x equals 1, y equals 2, z equals 3. It's on us to remember what order we had our variables set up so that the results are in the exact same order. This process works no matter how many rows, no matter how many columns you are dealing with. So let's take a look at one more example. And here we're going to look at a rather larger system. How about Here is a system of 5 equations with 5 unknowns. This is definitely at the point where I do not want to try to solve this by hand. But we're looking at 2a plus 3b plus c plus 5d plus 9e equals 12, 4a plus 7b plus 3c plus 2d plus 3e equals 10, 9a plus 9b plus 8c plus 6d plus 2e equals 7, 8a plus 3c plus 2d plus 3e equals 3. Notice there's no b in that equation. And 8a plus 4b plus 6c plus 2d plus 6e equals 5. If I jump back over to my Jupyter notebook, we can type all of this in. Again, remember, we want to look at the coefficients. So that first equation was 2a plus 3b plus c plus 5d plus 9e equals 12. The coefficients were 2, 3, an implied 1, 5, 9. So we have those in our first row. The constant on the right-hand side of that equation was 12. We have that down here. Then we put in the coefficients of the second equation, the constant of the second equation, the coefficients of the third equation, the constant from the third equation, the fourth equation, and the fifth equation. Right? 5 equations, 5 unknowns. Now that we have changed this cell, in order to get our calculation, we are going to go to runtime. We are going to restart session and run all. We're going to say, yes, we want to lose all of our variables because we wanted to change them. And then if I scroll down, it will have run my results here. And there is my solution. This time we have some ugly decimal numbers. That's usually going to be the case. Right? These are approximations. It's a little bit hard to say how I should interpret these because my coefficients were all whole numbers, exact values. But just for the sake of argument, let's round all of these to 3 significant figures. So I get that A is 0.784, B is 1.45, C is negative 2.02, D is 0.260, and E is 0.756. Right? Again, it's our job to remember what the variables were and what order we used them in. But since we had them all in the same order, we can interpret that in exactly that order. We can write all of that out, and there is our solution. If you want, you can plug all those numbers in and double check. You won't get exactly the constants on the right-hand side, but you should get close enough within 3 significant figures. Remember, close enough might mean off by 1 or 2 digits in the last decimal place. All right, I think that's enough for this video, so I'll wrap up with that. As always, thank you for joining me, and I'll see you next time.